In this lecture, we'll step back and take a big picture view of life on Earth. This is the tree of life, where the common ancestor is represented at the center of the diagram and genetic diversity in time moves outward. Most of the real estate of the genetic tree of life is in the form of microscopic organisms, or microbes. Plants and animals actually occupy a small fraction of the genetic real estate of life. We can also see other creatures like fungi, which have diversified and also adapted to their environments. The modern tree of life is mapped out using genetic material, DNA or RNA, and what we see is basically the gradual deviation of the base pair sequences in the genetic material. Doing it with genetic material means we do not have to depend on recognizing distinct species. In other words, the tree of life can only be constructed using body fossils for about 500 million years. But with genetic material, it can be reconstructed in principle all the way back to the origin of life, perhaps 4 billion years ago. There's no good time precision, though. As opposed to body fossils, which are minerals where radioactive decay can be used to date the minerals very accurately, genetic material divergence depends on an evolutionary clock that's not very well calibrated. So our time precision of projecting the tree of life back, especially billions of years, is quite poor. All of this information places us, humans, as a tiny twig on the tree of life in an overwhelmingly microbial world. Here is the modern tree of life with the root representing what's called LUCA, the last common universal ancestor, the hypothetical organism that was the first genetic information leading eventually to everything else. There could have been possible multiple roots to the tree of life, but eventually the most efficient organism proliferating would have dominated and prospered while the other died out or become food for the more successful organisms. So in this diagram, we see time going upwards, and the space horizontally is the genetic real estate of genetic diversity. This makes it clear that most of the genetic diversity of the Earth is contained in microbial organisms from two main branches, the bacteria and the archaea. The archaea were only discovered about 40 or 50 years ago, and they represent microbial and primordial life forms that seem to have prospered in the warm conditions of the early Earth. Cells with nuclei, eukaryotes, represent this branch of the tree of life, and you can see plants and animals as two small branches. Humans, in this diagram, are smaller than the dot on the eye of animals, indicating what a tiny fraction of genetic real estate us and even our ape ancestors represent. Here are now the words of Charles Darwin from his famous book, Origin of Species. Thus, the small differences distinguishing varieties of the same species will steadily tend to increase until they become equal to the greater differences between the species of the same genus, or even of distinct genera. This molecular tree of life is a fundamental piece of modern biology to tell us about the world we live in. Using the cytochrome C, we can look at the number of deviant nucleic acids which give us the genetic overlap. And as mentioned, our genetic overlap with our ape ancestors is 99%, with dogs 87%, but we actually share almost half our DNA with simple yeast. So the next time you look into your beer glass, you can acknowledge there's some kinship there. Here's a big picture view of the history of life on Earth, as well as we understand it, where we're representing geological timescale going back 4 billion years, or actually to the Earth's formation. The main geological eras are represented by the vertical lines, and we can see the increase in the Earth's temperature and oxygen content. There are features in this evolution that are notable, and they are the mass extinction events. A mass extinction event is a period marked by a rapid decline in biodiversity and in the number of overall living species. We have the best evidence for mass extinction, of course, when the fossil record exists, so only going back 500 million years. In this graph, we see the percent of extinction over cosmic time in the last 500 million years, remembering that much of this is measured in the oceans. And you can see the peaks correspond to mass extinctions. The largest mass extinction was the late Ordovician, about 440 million years ago. And there was another dramatic one at the end of the Permian era, about 250 million years ago. And then the famous one called the KT boundary at about 65 million years ago, corresponding not only to the death of the dinosaurs, but many other large mammals. Mass extinctions are similar to a natural selection of force that's applied to organisms, but in this case around an entire planet, not just in a region. All organisms are experiencing extreme environmental pressure during this time. Only the organisms that can adapt fastest will be able to take over the new ecological niches that have been vacated by the species that go extinct. It's a dramatic form of natural selection, playing out on short geological timescales. It's an ironic situation that mass extinctions in and of themselves are catastrophic to biodiversity because a large fraction of the species go extinct. However, the good news is that the possibility for new and innovative forms of life accelerates. So ironically, some of the greatest leaps forward in biological diversity occur after a mass extinction event. The current biodiversity on the planet is that all existing species descended from the 4% of the large species that survived the annihilation during the Permian-Triassic extinction. The current biodiversity of the planet is a testament to the resilience of life and the power of genomic evolution. What causes mass extinction events? It's not entirely clear, but one of the agents is clearly external forces, in particular impacts from space debris. Planets do not orbit the pristine vacuum of space. There's debris left over from the formation, and in the solar system, of course, there's the asteroid belt and various meteors floating through space. This debris is everywhere, and it collides with planets daily. The cratering history of the Moon and Mercury, planets without atmospheres, show clearly how much debris there is impacting over cosmic time. The Earth collides, for example, with about 100 tons of dust and small particles from space every day. Luckily, because of our atmosphere, most of these particles burn up in the upper atmosphere. That's what you see when you see a shooting star. A car-sized asteroid will hit the Earth about once a year, but most of them burn up in the atmosphere too. An asteroid the size of a football field, 100 meters or so, will come along every 2,000 years. This graph shows the typical time between impacts as a function of the size of the impactor. Basically, there's a logarithmic distribution of debris out in space, many more small pieces of space junk than large pieces. And so the small pieces of debris hit much more frequently than the large pieces, but do correspondingly less damage. If we scale up this and go to the high end of this range, we see that every few million years, the Earth is going to cross paths with an asteroid, maybe hundreds of meters across, that would have global effects upon impact. And such incidents, occurring very infrequently, can cause a mass extinction. We see evidence of impact, if not mass extinctions, nearby. In the Arizona desert, not far from where I live, there's evidence of a crater from an object probably 200 meters across that hit northern Arizona 35,000 years ago. The crater left by an object is much larger than the object itself, so this crater is 1 kilometer or so wide. Another evidence of an impact, or actually an explosion that occurred just before impact, is in Siberia, the Tunguska event of 1908. It's likely that it was a 100-meter scale object, possibly a comet, not entirely clear, and it was far from any population center because it was Siberia. However, the impact was such that it was read and triggered on seismographs around Europe, as much as 1,000 miles away. There was a more recent event in Russia also, the Chelyabinsk object, which was estimated to be 30 meters across, and it broke up in the atmosphere and fragments fell to the ground. These are relatively small events. The event that has been attributed to a mass extinction 65 million years ago came when around the world a layer rich in iridium of clay was found. In other words, a deposition layer of sediment where the rare radioactive mineral of iridium was found. Iridium is scarce on the Earth, but quite highly concentrated in extraterrestrial objects. So this was an indication that an impactor came from space. Another indication was shocked glass or quartz in these sites, and yet a third was a soot layer in many parts of the world, indicating global forest fires. All of this put together indicated that something from space hit the Earth about 65 million years ago, corresponding closely in time to a mass extinction seen in the fossil record. A couple of decades ago, scientific teams confirmed that there was a crater off the Mexican coast that age dated to the same time as the mass extinction. Interestingly, this neat story of an impact 65 million years ago and a mass extinction in the fossil record has unraveled slightly because the coincidence in timing is not quite good enough to attribute the extinction to the impact. It's possible there were global volcanic or geological changes around that time, and that life actually took a 1-2 punch from a combination of geological change and impact from space. This crater, now dated very accurately to just over 66 million years with an error of only 11,000 years, is attributed to an asteroid about 15 kilometers across. The energy caused by this impact at the likely velocity it was traveling in space is equivalent to about 10 billion times the Hiroshima first atomic blast, which is to say 15 trillion tons of TNT. That's an extraordinary level of destruction, far beyond the sum of all the nuclear arsenals in the world. Because it fell in the ocean, it represents a crater that was difficult to discover. It actually used cores from the Mexican oil company that had been hidden in vaults for decades before scientists got their hands on them. Such an impact would probably have vaporized the ocean, and huge amounts of rock pulverized into dust and girdled the planet in a shroud of dust and cloaking, choking gas, which likely cooled the planet and destroyed the food chain or the food web. So the mass extinction was triggered from below, with the loss of photosynthetic organisms and small creatures and plants, and then the larger creatures died because of that. We can look at the evolution of life on Earth in terms of the tree of life. The tree of life is a way of showing evolution from the genetic material itself, RNA or DNA. And unlike fossils, which only trace back 500 million years, the genetic tree of life allows us to go all the way back to the beginning, 4 billion years ago, but with poor precision. We speculate a last common universal ancestor from which all forms of life derive. In terms of the real estate of life defined in terms of genetic material, humans and even our ape ancestors occupy a tiny fraction of the real estate. We live in an overwhelmingly microbial world. This microbial world, which eventually involved complex creatures like us, was subject to extreme environmental change caused by external agents in some cases. And so in the fossil record, we see evidence for 5 or 6 mass extinctions, when a substantial fraction of all species on life were obliterated. These mass extinctions are likely caused by some combination of violent geological upheaval and impacts from space.